Swayam Prabha. Digital India. Educated India.
So, I want to continue from where I left off yesterday, and after the lecture I realized that I am not very experienced talking to students in high school, because I think in parts I could have gone fast. Okay? So, please, it's really not what I cover, okay? Because this is just to give you an idea. So, I want to recap some of the things I did and get on to doing one example of a very conventional way of doing an integral, and then I want to do a very different way of doing an integration. This is what I plan to do today. Okay? All right. So, yesterday what we saw was that a computer has a limitation, a natural limitation due to finite resource, and this limitation comes due to finite size of storage. And by storage I do not mean the hard drive, but it is the chip. Okay? You have 32 bits, okay? And at best you have 64, and that gives you the size, or what is called the word length. Okay? So, that word length is all you have in order to store information. All right? You can store it in different types, and when you store this information, that automatically puts a limitation on what you can do. Okay? So, the example of what we saw was in a very simple algorithm where we needed to find the derivative of a function at some point x. We see that we cannot determine this precisely. Okay? You all know that as you decrease this, because this, you have the math definition which just says that the limit h going to 0, f of x plus h minus f of x divided by h is indeed the derivative. Okay? But this limit is important. If I start with a finite h, I will make an error. All right. Now, one of the questions which is very interesting, which was asked to me, is why did I not work with the derivative of x? Or I could have just taken a derivative of a constant. There it would not matter. I took the exponential purposely. Why? Suppose I took a constant. The first derivative will be exact. It will be 0. There is no step size that will matter. Okay? Suppose I took x. Then the first derivative will work out very well, because there are no higher order terms. The function goes away, right? So, therefore, because these are cases where your error will be 0, because the error that you had was dependent on the second derivative or a higher order derivative. So, therefore, I had to go away from a polynomial. All right? That is why I expanded a function as a Taylor series, so that becomes another way of looking at this function. All right? And then I truncated the Taylor series so as to get different algorithms. Okay? So, therefore, as a function of this parameter h, the algorithm is going to improve, but there is an overall error which comes because I only have finite number of bits to store a number. This is all I wanted to convey. Okay? So, that the math that you do on a computer is very different from the math you know. Okay? One of the very interesting questions which tells you which almost predicts my age is the fact that I gave this example of 1 by 3, correct? So, I found it very interesting. 1 by 3, okay? 1 by 3, if I write it this way, the computer usually interprets this as an integer by integer division. An integer by integer division gives you an answer which is an integer, that is 0. Okay? This will not matter if you use higher level languages like Python. I think some of you pointed out to me, in Python that does not matter. True, because the language tells it. The language guesses that the answer has to be a real. Okay? and therefore it uses that fact. So one of the hard ways by which I learnt it, because I had to worry about this, is if I have to find anything that has a 1/3, for example, volume of a cylinder, radius r, height h. So then this is 1/3 pi r square h. The answer you will get will be 0 if you do it on a non-Python kind of environment, you know, the more archaic ones like C, C++, Fortran 90 and so on and so forth, this will give you a 0. So the way to overcome this is to explicitly say that this is a real by putting a point, or just do this. This will also work. All right. So basically another question that was asked yesterday is, when you work with something like Python, which is what most of you are familiar with, I suppose, you will see that you're using packages. Okay, you will call a package. So numpy is what you would import, and then you will call an algorithm to take a numerical derivative, integrate, solve ODEs and so on. So what is it I'm telling you about? I'm telling you what goes on inside the package. Okay? For many purposes, for many applications, especially scientific ones, you need to know what goes on inside the package. Because really, as a person doing theoretical physics, this computer is like my lab. Okay? So I need to know everything that happens inside my code. My code is an experiment. So I need to be able to tinker with the soldering of something. I need to be able to know how the electronics works, I mean as in a lab. So here for parts of a code or parts of a package. So therefore the speed and everything should be under my control, which is how one does scientific computing. Okay? So a theory, when you do theoretical work, especially in physics, this is true even in chemistry and so on, it is not always pen and paper. Okay, you start with pen and paper, proceed up to a point, then you will have an equation which you really wish can be solved analytically because there are no errors. But you will be forced to solve this on a computer. But that does not mean you can give any answer which has no backing from you to say that this is correct up to this precision. So that's why one has to worry about what goes on inside the package. Is my motivation clear? This is just to connect up with all the questions that I was asked yesterday after my class. Okay? All right. So now I want to say something about integration, because I started setting that up. I said that if I have to integrate a function, okay, so I'm going to call the answer for an integral as I. It is some limit a to b, okay, f of x dx. This is the integral I have to do. What will it give me? A number, correct? And that number is the area under the curve. So this function f of x is a curve in the f of x versus x plane, and this gives me the area under that curve. Okay? So this is what I had. This is some a and the function does this. This is b. I want to find this. All right? This is really the inverse problem, right? Because when you take a derivative, you're really looking at a local information of the function, and by integrating, you get something global. All right? So therefore, this is what I want to evaluate. So what does have you all done calculus or have some notion of calculus? Some notion of calculus, good enough. So, but you know how to find the area, right? If I have, you can think of it as an irregular object. If I have to find the area, then you want to construct somehow something regular. So what would you do? You will divide the entire interval into equal spaced points. Okay? So you choose n points. Okay? And the number of points n, so the step size, when I fix the number of points, I will fix my step size to be some b minus a divided by n. Correct? So then what do? After I do this, I draw these lines. Please let's assume they are all parallel and equal, because on the board my ability to draw is fantastic. Okay? So this is what it is. Now what do? You want to find this area, sum it with this area, and so on and so forth as you go from this slab to this slab to this slab all the way to B. Okay? Now, the error you make will depend on what sort of a regular polygon you are using here, what shape you use here. Okay? You could use rectangles, you could use trapezoids, you can use some other function as well. All right? And all of that amounts to asking, within this small interval, how do I see my function? You always make an approximation to the function as a polynomial, okay? Because you see, even the Taylor series, I truncated it, so that became a polynomial, correct? So therefore, I always will assume some polynomial. If it is a rectangle, it's a constant. If it is a trapezium, what will it be? Straight line, because between 2 points you want a straight line, okay? Then I can have a quadratic, I can have a cubic function. So with each of these, my errors will improve. All right, and the errors will depend on which parameter now? N. That is the most natural parameter to think of. You can also think of h, because h gives you this interval. This is h. But that's not very, I mean, you will think of h more for derivative than for an integral. All right. So you take an n, and the idea is, in principle, if I take n to infinity, it really doesn't matter how I approximate it. I can think of it as a constant, which is just the rectangle rule, and as I increase n, the h becomes very small, and I will get my precise mathematical definition, which is the integral. Okay? But as I already emphasized, you cannot do that on a computer. Just as there is a limitation to how small h can be, the inverse case, there is a limitation to how large n can be. Okay? What you will see is, as you keep increasing n, your algorithm improves, but at some point the inherent finiteness of the machine is going to kick in, and you will start getting nonsensical answers, in the sense that your errors will build up to such an extent that you will have an order 1 error, which means you don't know what you have got. All right? So always your error has to be less than the answer. So if you expect numbers, quantities of order 1, which means what? Something like 10 or 100 or something like that, you have to have an error smaller than that. What if you have a very small number as your answer? Error has to be at least 1 order or 2 orders of magnitude smaller. Suppose I have an answer which I know somehow it has to be 10 to the minus 3. My error cannot be 10 to the minus 2. That means, yeah, it has to be at least 10 to the minus 4, 10 to the minus 6, and so on. Okay? So therefore, this really matters what your answer is. Now, okay, so first let's do the simplest thing, which is to take, let's take, so this entire integral I, which goes from a to b, f of x dx, okay, I can write it as a to a plus h, f of x dx, plus a plus h to a plus 2h, f of x dx, plus etc., b minus h to b, f of x dx. Okay? I am going to call each of these guys as IH. So let's call it IH1, IH2, and so on. And this is IHN. So you add all these pieces, you should get the answer. So now, really, once we fix an approximation, when we fix an approximation for one piece, we fix it for all pieces. Okay? So now, let's take IH1, or rather any, let's take IH1. What is it? It's a to a plus h, f of x dx. All right? Now, how do you want to approximate your function? Think of your Taylor series. What does Taylor series tells me? If I have a function, I can expand it in the neighborhood of some point. I'm just going to take a small neighborhood h. Then this becomes the function itself plus h times f prime of x plus h square over 2 factorial f double prime of x plus etc. Okay? So therefore, I know that in general, I can expand my function in powers of some x. Okay? The x here is this. So instead of thinking of this function, it could be something complicated, right? So maybe let me rephrase it because I don't want to confuse all of you. So hang on, let me rephrase it. So suppose my function f of x, I do not know what I have the answer for, but he certainly has one answer. Suppose my function is exponential x. This has a series expansion. What is it? 1 plus x square by 2 factorial plus etc. Correct? So now the easiest is, let me take one value. Okay? Take it only as a constant, take it as a linear function, take it as a quadratic, and so on and so forth. Okay? This is for a function which I know. So if it is an arbitrary function, I will want some expansion like this: a0 plus a1x plus a2x square plus etc. This is my approximation. Where I truncate will give me one integration rule. Okay? So let's do the simplest. Simplest is leave all powers of x, take only a0. Okay? If I only take a0, what happens to this one? So let's do the first case. Which one? Let us do the first one, which is take f of x as a0. This is perhaps the worst thing you can ever do. You have suppressed all the dependence on x, which means here I don't care that this was rising, this was having a different behavior, this had a different behavior here, I don't care. I'm just going to pick up a value. Alright? So therefore, what happens to IH1? What happens to IH1 will also happen to everything else, right? So it is a to a plus h. Instead of f of x, I'm going to put an a0 dx. a0 is a constant. I can pull it out of the integral. All right. So therefore, this becomes a naught, a plus h into a plus h minus a. So it is a naught h. What can I give the value of a naught? Some constant value which corresponds to the function to be of some use. Correct? So the one value I can give is the value of the function at this endpoint f of a. Or I can give the value of the function at a plus h, or I can find the value at the midpoint. But no matter what, it just tells me how I am constructing my rectangle. If I give the value here, I have constructed a rectangle like this. If I use the value here, I have constructed a rectangle like this. If I use the value in between, I construct a rectangle this way. Okay? And as long as my h becomes small, none of this would really matter. All right? So where the function is less than the value here, of course it's going to matter. I mean, there is an error, but as you take your limit n going to infinity, all these errors will go away. All right? So that gives you the first rule, rectangle rule, which says in this rectangle, pick a value, you construct your rectangle. Usually the prescription is, you know from common sense, to choosing the midpoint is a good guess. Okay? So then I will fix my a0 to be f of a plus h minus f of a by 2, midpoint value. That gives me a0, but it's a number. All right? So then I can pull this number out and I get this guy. What will be the next one? The next one will be some other a0 prime, okay, whose value is f of a plus 2h minus f of h by 2. Okay? So that I will get this integral, the entire integral, as a sum of these pieces. All right? So then every interval has a value of a weight. What is the value? H. It's equal weight. All intervals have this equal weight h times the value, which is exactly the area of a rectangle. All right? So that is your rectangle rule. How do we do better? Let's take a straight line. Okay? So let's say that instead of working with the, so this, right? So instead of working with just one point, let's take 2 points. If I have 2 points, I can fit a straight line to it, right? So if I can fit a straight line to it, I have another rule that I will get. So basically you are going to approximate the function in any of these tiny intervals as a straight line. So you get the trapezium or the trapezoid rule. Alright. So now let us see how to do that. Now my f of x is going to be a0 plus a1 x. This is my approximation, right. So I have some x dependence here. So now I have to plug it into this IH1. This IH1 is going to be a to a plus h, a0 plus a1x dx, which is a0 if I integrate dx between a to a plus h plus a1 integral a0 to a0 plus h x dx. All right. What does this give me? This gives me a0h plus a1. What will I get? X square. Correct? So what is that? So solve and tell me. What will you get? You will have a0h square minus a0 square. Can you simplify? What will you get? This will be a0h plus a1 into a0 square plus h square plus 2 a0h minus a0 square, right. So these two cancel. Then I will have a0h plus a1 what? a1 a0 h by 2 plus a1 h square. That is it? Yeah. So now I am going to leave terms which are of order h square, because that is going to be small.
Shouldn't there be a by 2 then?
Sorry?
Shouldn't there be a by 2?
Oh, there should be a by 2. By 2, by 2, by 2. Yes, you are right. Yes, by 2. I forgot the 2. Yes, yes, it is important, because I seem to have, I have put the 2 here. So these 2 will cancel, no? Is this right? Yeah, this is right. So that I have a1 h square by 2. Okay, so a0 square cancels, and is it right? Hey, I made some mistake, boss, and I know where my mistake is. I made a mistake. See, that's the problem. I was wondering if I should even call these things a and a0, and I thought I was going to get confused, and I indeed did. This is an a and an a plus h. Sorry, sorry. My mistake. Did you see what I did? I put an a0 here because I started getting products of a0 and I wondered what the hell was going on. Okay, fine. So here, so this becomes an h, a1, this let me do slowly, x square by 2, a to a plus h. Okay, now this is a0h plus a1 over 2. Now it's okay. Now it's okay. This makes a little bit more sense to me. This is what? This has to be a square plus h square plus 2ah minus a square. So these two cancel, so that I have, am I right? Please check. This will be a0h plus a1 by 2, 2ah plus h square. Okay? All right. A is the endpoint, and a0 and a1 are the things I need value of. All right. So then this is what I have. Okay, great. So now I can then, this one I can ignore. Right? I can ignore it because it's an h square term compared to h. So therefore, I only have this guy. So now I have to really find out what a0 and a1 are. How do I find that out? Use the function. correct? So I can take my A0 to be f of A, and no, I can't do that. Wait, let's see. So I can take f of A, I have to fit it, right? So A0 plus A1 into A, and f of B, f of A plus H is A0 plus A1 into A plus H, okay? So now I can solve. Can you solve for A0? If I solve for A0, what do I have? A0, so let me do it. Okay. So now I want to solve for A0 and A1, okay? So what would I get?
You just substitute 0 into everything.
You can substitute, why do you want to substitute 0?
So A1 and 2 get cancelled, so you have only A0.
You can, no, why? That is one way of determining it, right? When you, no, but why would I take x to be 0? Because I need it only between A and B, no? Why would I take 0? I didn't understand. Why? You want to put f of 0, but why, where does f of 0 come? Because I have an A and a B. Unless and until I have my A itself to be 0, that will make sense. Okay. So therefore, I have to now solve for A0 and A1. Okay. So if I solve for A0 and A1, then I can plug it into this equation. Okay. So what should you get? What should you get? You will have to get A0. Can you solve and tell me and substitute? What would you get? 1 minute. Okay. So what do you get A0 as? You found A1. Okay. Tell me what is A1, A0, f of? By H. A0? You have to subtract, right? F of A minus A1 divided by A. Correct? So what do you get? Figure out, and then what do you have to do? Plug it back into this formula, right? So why don't you tell me what A0 is, and then tell me what this formula would be. So you have A0H plus A1 by 2, 2AH. But maybe I need my H square. I need my H square because I have a factor of H here. You see, I can't leave it out before. I will need my H square. Correct? Because your A1 has a factor of H there, so I cannot possibly leave that. Okay? So I have 2AH plus my H square because A1 already has an H. So therefore the H and H will cancel, then the H square will cancel with the H to give me all terms of order H. That's all I want in the end. Okay? So now what do I get? Plug it in and tell me. It's a simple enough thing to solve. So let's do. What is A0? A0 is f of A minus A1 into A. So what is that? You put it back into this. So then this is going to be, we can already put this, I think this is the easiest to do. So that I'll have f of A minus A1A into H plus A1A H plus A1 H square by 2. Okay. So f of A into H minus A1A into H plus A1A H plus A1 H square by 2. Okay. Now let's plug in A1. If you plug in A1, what do I have? This equation becomes f of A into H plus H square by 2. What is A1? F of A plus H minus f of A divided by H. Okay, so now you see I was going to I threw away the h square term and then I realized the a1 has an h. I can't throw it away. All right. So therefore, when I do this, then what happens? F of a into h plus h by 2 f of a plus h minus h by 2 f of a. So, h by 2 f of a plus h by 2 f of a plus h, which I can write it as h into f of a plus f of a plus h by 2. What is this? Area of a trapezoid, trapezium. That's all I did. Okay? Okay? So, all we did was we approximated the function as a0 plus a1x and put it into the IH1, and then we have to determine a0 and a1. So, we did the whole manipulation with respect to a0, keeping a0 and a1 constant. Of course, I very quickly said, let's throw this out, but you saw it's an error. If I did that, it's gone. Okay. The other way you could have, there is one more way in which you can check this. Suppose my endpoint A was 0, then this just collapses back to the rectangle rule. So, I better keep my h square. Okay. So, now you keep that, you find a0 and a1. All right. So, then you have f of a plus h. You solve because two equations, two unknowns. Your two unknowns are a0, a1. All right. You find that and you see this nice rule come up. So, what is IH1? IH1 is h, which is this breadth, times f of a plus h by 2. That is the area of the trapezoid. So, what have you done now? You are taking the function and taking each area, I mean each tiny piece that you have divided the function into in the form of a trapezium. So, this is how it looked like, right? B, A, all right. So, you took a point here, constructed a trapezium, then you took another equally spaced point, constructed a straight line, trapezium, took another point, straight line, trapezium, and so on. In the limit where the number of points you have chosen equally between this interval a and b, when it goes to infinity or h goes to 0, this becomes an exact way of evaluating. Also, because this function is a linear function, all linear functions will give you exact answer. For instance, if I integrate x between 0 and 1, I will get machine precision, you will get the exact answer. But if I do x square, I won't, right, because I need the next term and I have thrown that term, I have now truncated the term, right. F of x itself is a0 plus a1x, but if I keep a1x square, I can integrate up to a quadratic, all right. Okay. So, on the other hand, if it is going to be the beast like exponential x, then all of these will give you an error. Okay. Now, I want to show exactly what we saw yesterday. I will just show this and then move on to a very different way of evaluating a similar integral, okay, which is in fact a very fun way which uses probability. I think this is where it is. Is it coming up at all? It's coming up there. Okay. All right. Evans. Okay. So, I seem to have, okay, so I pulled up something which I knew I had from before. So, you see this line here is obtained by integrating, I think I forget the function, very likely it's e to the x, I have to look at the code, for two different algorithms. One is the trapezoid rule and the other is the Simpson's rule. Simpson's rule approximates the function as a quadratic function, but then takes a symmetric interval, because after all any interval a and b you can always define, you can define the endpoints and make it a symmetric interval. But no matter what, I want to draw your attention to the fact that after a particular n, you see this jumping around of the errors. In fact, he has coded this trapezoid rule, taken it as a trapezium, and he too notices that first it goes down like this. Here the trapezoid, because this it's still improving, the n is still improving, the errors are going to kick in much later. But here the improvement is drastic, right? You see how quickly it falls to almost machine precision, and then if you keep increasing n, it jumps around. So this illustrates the fact that while this is not for the algorithm, I couldn't, well, I can pull up the data and then plot it and show you that it will go up, but the most important thing is this illustrates that arbitrarily if you increase the number of points, as you would naively think, if I want to do something accurately on a computer, I'll think, oh my god, I have to increase n. If I keep increasing n, I'm going to get good answers. The answer is no. You'll in fact start getting bad answers, and this can potentially increase. It can go all the way to an order 1. Again, to remind you, what is my relative error? This is again a log and a log, okay? So the relative error is defined by this difference, okay? This is an important thing always, no matter what what algorithm you have, you always want to calculate a relative error, because it tells you how an algorithm is performing with respect to the parameters that control the algorithm, okay? So then I define the relative error as the absolute value of the numerically computed answer. So numerical answer minus exact answer, okay? So that's why instead of numerical answer I put derivative calculated yesterday, okay, which I said dir calc. That's because of using variables on a machine for a long time. I immediately write it as dir calc. So this is the numerical answer minus the exact answer divided by the exact answer. So this is calculated by a machine. This is something you know, okay? One of the questions which was asked is, why do you want to do it? I for x e to the x, I can always find the derivative, I can integrate, I can do whatever I want. It's just such fantastic functions. Why should I even put it on a computer? It is not so much to test the computer, but to test your algorithm. If you have to test your algorithm, you better know that your algorithm does simple things first before you give it something for which you don't know what to get. For example, when you in physics research, often I end up with functions. I don't know its functional form. I will only have a set of numbers. So then what do I do if I have to find the area? I have to use one of these integration routines. Okay? Some of these integration routines will want the value of the function between 2 points which are not on the grid. So between these 2 points, what do? Interpolate. So things like interpolation, differentiation, integrations, all of these are sort of necessary in a toolbox to do any kind of scientific study. Alright, that's what I wanted to illustrate. Now, I want very quickly, I am going to show you a very different way. So this you understand, right? In some sense, you take the interval, divide it into endpoints, and then you approximate it by some nice geometric shape, and then you add the areas. Fantastic, okay? But what this also tells you, that any integral, which I call a to b f of x dx, can be approximated as some 1 over n summation function evaluated at discrete points times the weight, right? For the simple, which rule did we do first? We did the rectangle rule. This weight was just h. Whereas the trapezoid rule has an h by 2 and an h by 2 for each. So when it overlaps, only the endpoints have a weight of h by 2, intermediate points have a weight of h. Okay? So then you can write this program to figure this out. Now what I am going to do, I want to now do a different way of doing an integration, which is I want to approximate the function where the weights are going to be some probability. Think of it as a uniform probability. This then is the average value of the function. If the weight is going to be some 1, or some h, and I am going to bring that h out, or even think of it this way as a constant factor h. So then this whole thing I can think of it approximately as the mean value of a function. What will the x's be? They are randomly drawn points. Okay? I draw the points randomly, give the same weight, so I can in fact set my h to be 1, I don't care. This then is the mean value. Okay? Sample, find the value of the function at all these randomly drawn points between this interval a and b, and I'll find out what the average value is. That gives me another way of doing an integration. So I just put h to be 1. Okay? You can have an h, because if it is 0 to 1, you don't need the h. If it is going to be something different from that, you can rescale it by putting the h in, because this will go into, so if I have, what I can do is, I want to do this, right, times p of xi, correct? But if it is a uniform probability between 0 and 1, this becomes 1, this becomes 1. If it is any other interval, what will this probability be? 1 over the interval. So this will itself become 1 over h. Okay? So this probability, if it is uniform, it is just 1 over h. Okay? Because this is just a small interval. If it is the entire, so here I should say a to a plus h, please. If it is the entire one, then what will it be? This will be b minus a, and this will also be b minus a. All right. So therefore, this is another way of doing this integration, and I am going to demonstrate it in a different context. Okay. Instead of doing it as an algorithm, let's do it as a game of throwing darts. Okay. And the connection to integrations is as follows. Suppose I want to find the area of a circle. Okay. I want to find the area of a circle. Hopefully I can draw a circle of some radius. Does it look like a circle to you? Let's use some imagination and think it's a circle. Okay. So this is a circle, and let's call the radius r. I want to find the area of the circle. This is a two-dimensional integral, correct? I have to integrate x, I have to integrate y with the limits, or do it in terms of r and theta, right? Because this goes from 0 to r, theta 0 to 2 pi. So it's a two-dimensional integral. But I'm going to do it by playing darts. How? I will inscribe it inside a square. Again, imagination that this is a square. Okay? This side 2r, this is 2r. So how will I find the area of the circle? I just have to shoot darts at it. Okay? Let's assume I'm such a good thrower that it will not leave the square, because that also can happen. Okay? Or somehow I have this tunnel which allows me to only throw darts at this area. I keep throwing it. Some of them is going to fall inside the circle, some of them outside. So what should I do? How will I get the area?
Well, we can see how many fell inside the circle divided
By the total number. That gives you a probability, correct? That should give you an area. Okay? And I already know what is the area of a circle. The area of a circle is pi r square. So if I keep pi as 1, I can also evaluate pi. Correct? If so, not pi as 1, I'm sorry, r as 1, sorry. Sorry, I think all of you think, what is she saying? Yeah, sorry. R as 1, I can evaluate pi. Okay? So that is the idea that we are going to use in order to do this integral. Okay? So instead of doing it as a 2D integral, we are just going to throw darts. So let's see how to throw this dart, and let's see how much of a good estimate of area we get. Okay. So how many times you want to throw? How many? 10,000? Shall we start with 100 just to see? Okay, 10,000 will work, but let's do 100 first, if you don't mind. Okay, so now you see, you get all this. This is randomly thrown. Okay, now the diameter is 2. Okay, so the radius is 1 here, because I want to get an estimate for the area. Okay, area as well as an estimate for the pi. So you see, for pi I got 2.88. That's bad. Okay, so I need more throws. So let's do 10,000. Okay, all right. All I am doing is to just find the geometric probability, which is just a number that's fallen inside divided by the total number. All right, and because I have chosen the dimensions appropriately, I seem to have got an estimate of pi as well. All right, so then that is 3.1. Okay, now how do I improve it? 1 lakh. Okay, 1, 2, 3, 4, 5. Okay, all right. It'll come, just give it some time. More than this, they can try. You want to do more than that? Yeah, all right. Now, so here the estimate of pi, look at how it has improved, 3.14. So you've got 2 places. Okay, so for 100 you didn't even get the first place. For 1,000, you said 1,000, right? 10,000, yeah, 10,000 you got. Hey, we should see 1,000 also, what happens. Okay, in between, why not? Why not? So we did in steps of 10. So let's do 1,000. It's going to be bad. So you got 3. So for 100 you didn't get the first place. For 1,000 you got the first place. For 10,000, first place after the decimal, so 3.1. Then 1 lakh we got 3.14. You want to do more? 10 to the power 7. I don't know if it will, I mean I'll let it run and then it will plot slowly. Okay, 1, 2, 3, 4, 5, 6, 7. Okay, it will come. Which one? Yes, that's my assumption. Otherwise I will lose, right? That's why I said I'm going to assume that this is some kind of a tunnel where if I start shooting, so it's just some gun there, I shoot it, it only falls inside, it doesn't hit any sides, I don't lose a single thing, and all of them fall here. Has it come yet? No, it'll come. So all of them fall here, and all I have to do is to take the probability of something fallen inside to the total number that I have shot. And by choosing my R appropriately, I also get an estimate for pi. So this also tells you that this guy converges slowly. If I had to do the integral, I would have got an area of pi r square, set r equal to 1, the answer itself would have given me pi, and I would have got up to 15 places after the decimal. So the question is, why do you do something like this? It's a nice fun thing, but why should you even consider this as a good algorithm that one has to work with? The answer is, many times you have integrations which involve several dimensions. For instance, area itself has 2 dimensions, volume 3 dimension. Okay, sometimes you might have to calculate an integral of several variables in 2 dimensions. Okay, what if I have to integrate over 2 vectors, 2 volumes, you know, some d3 v1, dv1 dv2, that is going to be a 6-dimensional integral. Suppose I do something like this simple integration algorithm, per dimension I will have some error, and as I increase the dimension, it will be raised to the power of the number of integrals I do. So at some point I will end up using million points or something like that, but then not get a very good answer. Things like this, once I use probability, there is a very powerful theorem that kicks in, which is called the central limit theorem, which is, as I increase the number of trials, then any distribution goes over to a Gaussian distribution, and I know the error. It has to go as 1 over square root of n. That's the power that we are using here. Alright. So, this convergence is very slow, which means what do I mean by convergence? How quickly I get the decimal, the places in pi is very, very slow. Alright. But the errors that you get does not depend on the number of dimension, because if I have a 6-dimensional integral, I will calculate all this, I will calculate 6 random variables. I can use my computer to generate random numbers, take 6 random numbers, sum the function and divide it by the total number of such times I have evaluated the function. Alright. So, I can work with a million points. Not only will the program run fast, of course it will run very fast because I am taking all the dimensions together. What will happen is the errors do not depend on the dimension at all. I will get a 1 over square root of n, and n has to be large because it is a multi-dimensional integral. So, therefore, I still use the same number of points as I would normally use, but I do not have this deterioration of performance with the number of integrals I calculate. Okay. Sorry? Central limit theorem is that for large number of trials, any distribution goes over to a Gaussian distribution. So, you take a binomial distribution, you increase n, the n going to infinity limit is a Gaussian. Okay.
Suppose if we increase the radius, does it have any impact on this calculation, like does it take more tries or something?
Yeah, it depends. Well, I don't think so. So, here you won't be, if I change the radius, then I will have to scale it by r square to get my pi, for example. No, it won't matter. It just, you will have to scale the random number, because whatever you get between 0 and 1, you will have to now scale it between 0 and r. It only marginally affects it. It won't be too bad. Okay. Yeah. It's still loading. Yeah. It aborted. Where did you see? Oh, yeah. Anyhow, tell me.
Ma'am, so you ran the program for 100,000 means different powers of 10. So when you started with 100, you did not even get the first place.
No.
With each succession, you got
one place.
But then when you did
after a point, it's not even changing. Yeah, there's no guarantee because its convergence is very, very slow. This is what I'm trying to say. Not necessarily. I can perhaps it stops there. Perhaps it improves slowly with, I need to increase n by some more before I get an improvement. But this shows that it will move very slowly, right? The convergence to the actual answer is very slow, okay? Because the number of dimension is less. And really this is not meant for, it won't perform as well as just doing the integral. For instance, I could have done the integral 2D integral very quickly by integrating in x and y or r and theta, and I will get pi to 15 decimal places, no doubt about that. Okay. But where this actually wins is the fact that although it converges slowly, there are tricks you can do. Okay, this I did in a very crude way. There are tricks you can do to make it work better. Okay. And no matter what, it only wins because the errors do not have any dependence on the dimension. As you increase n, it will always go as 1 over square root n, which is given by central limit theorem. Okay. So, this is just to demonstrate that apart from your conventional integration routines, you have very different ways of evaluating something numerically, and each of these are extremely powerful in its application. Yeah. Okay. So, first, that's not even of much use, because even if you did it, you have done it only as an exercise. Okay. If I needed pi, I will need pi at best to 12 or 15 decimal places. Why? There has to be some, no, there should be a way. I don't remember the way. I don't know the answer to that question. Okay, but certainly not this. And if you ask me whether, yeah, so I don't know. So there has to be some way of finding that out, but yeah, there are also, okay, so I have to say this. So this kind of thing where you inscribe, so what is it you're trying to do? So I thought of one way, okay. So maybe you will have a lecture where you can estimate pi in different ways. Okay. So one way is, suppose I have this circle, its circumference is 2 pi r. Okay. So now I inscribe it inside different polygons, triangle, square, and in general n-gon. As n increases, it should go as a limit to the circle. So therefore, by using that idea, I can keep increasing my n, and I have to find the perimeter of this polygon. So that way I can improve and get pi. In fact, there are algorithms which will do that. Okay, I think it will still work with this. All right, not necessarily throwing dart, but by using the fact that the perimeter of a polygon, as I keep increasing n, has to end up to that of a circumference of a circle. Okay.
So computers have like a specific limit to how small a number they can process. So when you're drawing a circle, the circle there will be slightly jagged.
Yeah, always.
So will that contribute any significant?
No, no, no. Anyway, any graph that you see that is plotted is obtained by interpolation. Okay, because always your computer will evaluate the function at some discrete points. You have so many plotters, right? Even on your cell phones you have plotters. If you ask it to plot something, it only evaluates it at discrete points and then finds a curve. And there are very nice ways of interpolations, including a probabilistic way to do interpolation. All right. So these concepts that you have in probability, in math, whatever, in different areas, is something that you would always use when you think of what lies inside the black box that you call when you use something like Python. So next time you use any module, you must think that what goes inside it is something that's very interesting. All right? Yeah.
As you increase the number of sides that enclose the circle,
you will come closer to.
How do you come at it?
I don't know the algorithm, but I know that there exists an algorithm because I recall a couple of years back I was doing something with someone and I remembered I did this algorithm for them. There are so many ways of doing it, okay? But the principle is the same. The principle is you take a circle, you inscribe it inside different polygons and you find the perimeter of the polygon. Then that will tend to this one. So then there are okay. So I do not recall as such, but I know that the different algorithms will determine how fast it converges to that of a circle. And hence, if I take r to be half, in this case I will get pi, estimate of pi. Correct? So that's what I'm trying to say. So I do not recall the algorithm, but the principle has to be this. Okay? Yeah.
So I remember reading about this algorithm. The way it's done is you have the larger square or any inside a polygon, and you also have a smaller one that is fully inside the circle.
Okay.
So pi will be somewhere in between.
In between, yeah. Okay, fine. Yeah. All right. Then I think I saw some other algorithm which did it differently. I don't remember now. I just don't remember. Maybe it was this. I don't know. I don't recall.
There's also like a series which I read about, which is where you sum 1 over the square of every natural number and that gives you pi squared over 6.
Yes.
So from that they calculate pi.
Absolutely. That's your zeta function. Yeah, sure.
No, but wouldn't that calculation also have
Sure. Which one? With series, absolutely. Okay, that's a fantastic question you asked. So yes, anytime you have to sum series, okay, so that will have its own beasts because you have something which goes as 1 over n, correct? As n increases, this number becomes smaller and smaller and smaller. All right. So one thing is when you are summing a series, something from, so let's say we even take something like 1 over n. 1 over n diverges, so let's take 1 over n square. 1 over n square. When you do 1 over n square, this gives you what, pi square over 6 or something like that. So then this is your, so when you sum over 1 over n square, you can start with n equal to 1 and go on to infinity or to some n, say on a machine. Now what will happen is on a machine an infinity does not make sense, so you will have to sum it to some large n. So you will know that the sum has converged by looking at the behavior. As you increase n, you see if it has reached the asymptotic value. All right. In other words, it should plateau as a function of n. Your series will increase and then it will plateau. All right. That is one way. Now sometimes you may see that it will plateau before the right answer. That is because you are adding to something large very small values. So it won't take that into account well. So then the the workaround is to sum from n to 1, the opposite way, so that you start combining numbers which are equal, they will add up to something large and then give you 1. Okay? So in other words, what I am trying to say is that what I expect on a computer, suppose I sum n equal to 1 to infinity, so 1 over n square. On a computer, this itself becomes some capital N. Alright? So what do I expect? In general, I expect that I will take an n1, I will take an n2, I will take an n3, and then I will see that it will start to saturate. But it may saturate to the wrong value. So how do I fix that? The problem arises because to a large number, I am adding smaller and smaller and smaller numbers. So it does not see the smaller number, effect of the smaller number. So if I now change the direction, instead of adding it from 1 to n, do n to 1. Then I will start combining small numbers which themselves will build up to large numbers, and then that I add to 1. So then that will converge to the right answer. But you also have alternating series, I mean series which have plus and minus. There you have to be careful because you have subtractive cancellations waiting to happen. Then you have to think of different ways. For instance, you can separate the pluses and the minuses and add together, and so there are techniques. So when you sum series, you have to worry about it on a computer. Anything you do on a computer is a cause for worry. So now I should have made your life more interesting, and next time you touch a package, you don't know what beasts lie within. Alright, so with that I stop. So thank you very much